And we are live. Welcome to this 33rd ElaadNL Webtalk. This is the 5th one we do in the English language. My name is Erik van Kaathoven. I work as a communications officer at ElaadNL. And Elaad is the Knowledge and Innovation Center of smart and sustainable charging of electric vehicles. And we are an initiative of the joint Dutch grid operators. Today we have two speakers, both from the Technical University of Delft. We have Jianning Dong. Welcome, Jianning. And Pavol Bauer. Welcome, Pavol. And they will give the presentation about wireless charging of electric vehicles. What is the current state of art and what is their outlook on the near future? So you can ask your questions during the web talk in the questions box of this tool, this webinar tool. You can also, it's perhaps good to know that we are recording this one, and we will be putting it on YouTube later. So this will be available on YouTube. And now let's just start. I'll give the floor to Jianning and Pavol. Good luck.
Yes, good morning, ladies and gentlemen. Welcome by this webinar. It's our honor to present our research results here in this forum. I would like to start first mentioning that we are already creating a MOOC. Please, next slide, Jianning. We created a MOOC of electric cars. It's a professional certificate program. You can join it for free. Unless you want a certificate, it's really for free. It has 4 parts. General part with introduction, technology, business, and policy. The uniqueness of this approach of explaining e-mobility and especially electrical cars is in combination of these 3 aspects: introduction, technology, business, and policy. And we are trying to connect them together, connect the dots. So it's a very attractive MOOC. So far, about 200,000 students and people took it with 10,000 paying customers. So it's also interesting from the financial point of view. So please feel free to look for it and take it to get more knowledge on electrical vehicle charging, and also contactless charging is briefly mentioned there. Next slide, please. So the first question which we always get is wireless charging really efficient? There are some pessimistic views on this, and I would like to remove your doubts and explain you why is it efficient. So first, conductive charging is usually connecting the grid in 1 phase or 3 phase. There is a rectifier point, there is a box of AC-DC converter, which is rectifying, and then there is an inverter with a high frequency transformer. This transformer is needing to create impedance between the charger and the power grid to have a galvanically isolated charger. And this transformer is hidden in the charger itself. It's a small component. There is an inverter, a rectifier, and then we have a battery. Efficiency of this kind of solution is for each step about 99%. So total efficiency would be 96% if you calculate it in 4 steps. And reality is about 95% end-to-end from the source to the battery efficiency. If I compare it to the wireless charging, actually all the steps are very similar. So we have a rectifier, we have an inverter, only the transformer is an air core transformer with large distance between the primary and secondary. So if you take a transformer apart, the primary and secondary, you create a large distance, then you get this wireless charging. We are talking about distances of 15-20 centimeters. And for that, you need to have this wireless transformer, which behaves as a regular transformer, with difference that leakage field, the leakage inductance is much bigger. And that's why we have a so-called compensation. You can see there's a capacitors added on the primary and secondary side. And the goal of these capacitors is to compensate for the larger leakage inductance and actually delivering reactive power to the transformer. The 2 compensation states can be done by different ways. So the high frequency transformer is about efficiency of 98%. Total efficiency is 95%. The reality is more than 95% end-to-end is possible. What we reached, you will see it on the results, is 97.4 from DC to DC. That means without rectifiers on the and inverters on the both sides. Next slide, please. So this is the theoretical answer why space does not introduce additional losses. It's a fact that electrical power is always transferred by electromagnetic fields instead of a wire. And this is the misunderstanding, miscommunication between the people who are not from electrical engineering. So you can see here that wired power transfer and wireless power transfer, it's only the difference in the air gap. So the efficiency doesn't need to be that much different in principle. Next slide, please. So I would like to comment our history of wireless charging in the DCNS group. Our group is called DC Systems Energy Conversion Storage, and storage is also electrical vehicle with battery on wheels. We started actually around 2002 when we first designed a wireless Christmas tree. The idea was to supply the Christmas tree bulbs with the wireless charging, and we succeeded to 1.5 meter Christmas tree without too much knowledge on this. The first PhD was Frank van der Pijl with the on-road charging prototype. We started in 2009, finished in 2013, and what you can see is this kind of snake where we could connect anything from the point of view of the loads. And we didn't think about the electrical vehicles in the first place. It was more general charging principle for wireless charging. In 2015, PhD of Prashant Venugopal, conceptual study on road charging. You can see on the picture that he was counting on the cables in the ground, not in the charging spots, but in the cables in the ground. And it was the first concept for on-road charging. 2017, we expanded it to the e-bike contactless charging with some patents. By the way, we have several patents for also contactless charging and on-road charging, which are covering different aspects and different questions. 1.2 kilowatt charger for electric vehicle was designed by PhD of Shomo Bandyopadhyay. 2019, startup Tyler started to market the charger for bikes. It's now a successful company with a lot of pilots, and this charger for bikes is already on the market. At the same time, we designed 7.7 kilowatt prototype for charging of electrical vehicles, which was in 2021 reaching 97% efficiency, actually 97.2 efficiency, and it was also expanded by reconfigurable charger with Francesca Graziano as a PhD student, where we are counting on patented solution, which we can charge also batteries for 400 volts as well as 800 volts. That means thinking about future. And now we are working on dynamic charging. We built up a track, 5 times 2 meters, where we can test this dynamic charging. PhD student of Wenli Shi is now working on it, and we have a 50 kilowatt prototype from Calvin Rickerk, which we want to scale up to 200 kilowatt for charging of the buses. Next slide, please. This is showing some of the setups, and I think this is the point where I pass the word to Jianning. Thank you.
Thank you, Pavol. So from the moment I will take over. So this slide here shows all the setups we have in the lab for wireless charging. So on the top column, top row, you can see these are the stationary chargers varying from 7.7 kilowatts to the future 200 kilowatts or even above. And then we also have the on-road charging setup, and the vision for us is in the future we will have this future energy highway equipped with dynamic charging coils. Apart from that, we also work on the grid interaction and efficient power flow control using DC-DC converters together with the wireless charger. You can see for the DC-DC converter we developed, it can already reach the efficiency of 99.5. And this power flow controller is suitable for the V2G application. And this slide shows the latest 20 kilowatt wireless charger we developed. Pavol already mentioned that the efficiency from DC to DC is above 97%. Even under the misaligned condition, the efficiency is still above 94%. That is really impressive. If you want to know more, you can read the paper we put here. Then I will summarize the state of the art of wireless charging in industry, and I will talk briefly about some public concerns, like is it really safe to use wireless charging, and are there any measures to solve these safety-related issues. So first, from the industry, actually, well, the stationary wireless charger up to 11 kilowatt has already been standardized. For higher power and dynamic charging, there are also many industry efforts developing them. So the available standards for the stationary charging are listed here on the screen. So we have the standards from IEC, ISO, and SAE. In these standards, it's already regulated the frequency range. So the nominal frequency for wireless charger now is 85 kilohertz for electric car. And this frequency is tunable in a band from 79 to 90 kilohertz. Also the power classes, the distance classes, and the offset allowances are regulated in these regulations. And more importantly, the interoperability between different types of coils are also regulated here. There are reference designs available in these standards. So if you follow the reference design, you will reach a standard coils which can be used for wireless charging. You can see in industry, the stationary wireless charging is actually already very well developed, but for heavy duty charging above 20 kilowatt, well, we need to do more research and development. Then I would like to address the problem related to the safety. So we know that the wireless power transfer for electric vehicle charging operates based on the magnetic field. So a lot of people are concerned about the electromagnetic radiation. Here it shows the full spectrum of the electromagnetic field from 0 hertz to the, well, very high frequency like the gamma rays. And the image here is from the US National Cancer Institute. As you can see, our visible light from the sun is also electromagnetic wave, and it only occupies a very narrow band in the full spectrum. The ionized radiation above this ultraviolet electromagnetic wave is harmful to our health because it can damage our DNA inside the cells, and it might lead to cancer. But it's not always bad. We can use X-rays and gamma rays for medical applications as well. Then we have the radio frequency, which is below the infrared light. The radio frequency is in megahertz or gigahertz range, and we are familiar with it in many devices like the TV broadcast, radio, mobile phones. So it's everywhere now for this radio frequency radiation. Then the wireless charger actually operates far below the radio frequency. The fundamental frequency, as we mentioned, is 85 kilohertz. It might contain some harmonics, but both the fundamental and the harmonics are below the radio frequency. And this does not have any ionizing effect on the human body. Well, this frequency is also used in other applications like the induction cookers, ultrasonic cleaners, and the power supplies for our daily consumer products like cell phones. So they do not have any ionized radiation problem to the human body, but it does have some impact. For example, if we are sitting close to the induction cooker, we can feel the heat from it. That is because of the radiation. And so if human beings are exposed to the low frequency field, well, because our body is made up of charged particles, so there will be circulating current induced. And this can heat up our body tissue, it can also heat up animals or electronics or any other metallic objects. That's why it's necessary to do the shielding to make sure the magnetic field does not leak too much to the external world. And we do this shielding so that we can avoid the body or object heating, and also to protect our electronics. For example, people who are wearing pacemakers should be careful with this kind of magnetic field, because it might affect the current circulating inside the pacemaker. There are standards to regulate how much magnetic field can be exposed to the air. So the guideline proposed by the International Commission on Non-Ionized Radiation Protection is the industrial standard every company has to follow. And this guideline has already been implemented in the aforementioned standards for contactless charging or wireless charging. So as you can see here, it regulates both the magnetic field and the electric field. So if you are curious about what these regulations say to us, please feel free to download the paper on the bottom of the screen. We did a survey 2 years ago about these standards and the limits. Then it comes to the question, how we do the shielding of the magnetic field so that it does not leak to the external world. You can see on the top, that's the structure of the wireless charger we are developing. We see the coils. These coils are the sources to create the magnetic field. Then we have the ferrite on top of the coils. And these ferrites can create a path where the magnetic flux prefers to go. So in this way, the flux are constrained by the ferrites instead of going wild into the air. To reduce the leakage field even more, we could also put copper or aluminum shielding plates. Because of the Lenz's law, the induced current in these plates will not allow the magnetic field to penetrate through them. So we have like a double safety measures to deal with this problem. And we did some simulation with the coils available in the standards. We can see the leakage field is actually significantly below the guideline. We also did our measurement with our setup. You can see on the left, it is far below the regulated 27 microtesla. So what we measure here, 30 centimeters away from our charger, is only around 11 microtesla. It's way below the regulation. So it is really safe. Then it comes to the question, how we take all the measures together to result in efficient and safe design. Well, we have to deal with the many design requirements, like the size available is limited, the efficiency should be high, the EMI or electromagnetic interference should be met so that it doesn't affect other electronics like the pacemakers. And safety issues, we are also facing thermal limit because it creates heat in the meantime. And more importantly, cost-wise, it should be affordable. So it's like the law of conservation of misery. We have to do the trade-offs. So what we do here is we first set the design space according to these requirements. Then we implement our physical models. Then we implement some search algorithm to search through all available candidates so that we can achieve the best trade-off. So the right-hand side shows the so-called Pareto fronts we obtained from our search algorithm. The star point is the one we choose for the final design. It can achieve a good trade-off between the efficiency and the power density for both the aligned and the misaligned case. The paper on the screen, on the bottom side of the screen, shows this approach. Then I would like to end the presentation with some outlook. Well, so far we are just looking at the stationary charge up to 20 kilowatt, but in the future we can have the so-called dynamic charging for the taxis or the electric buses. On the left, you can see a concept from VJCT. It's dynamic charging of electrical taxis at the airports. So while the taxis are waiting for passengers, it can be charged by the wireless coil, and these taxis are still free to move while being charged. That would save a lot of hassles. And for the buses, there is a research project going on sponsored by European Union. And well, TU Delft in this project is working together with ElaadNL to develop a 200 kilowatt opportunity wireless charger for electric buses. So opportunity charging means when the electric bus stops at the stop, we can use that very short interval to do the charging at a very high power, so 200 kilowatt. And the prototype for these charging modules will be ready in Q2 of this year. Then we have the railway application. So not only for cars or buses, we are also outlooking to the railway application. So on the top, you can see this is a demo project in Beijing. The rated power is 600 kilowatt, and it is used to power the tram. So in the future, we can have the tram without either pantograph or catenary. So we don't see the pantograph on top of the tram anymore in the future. And this research is done by our visiting scholar, Yi-Wang, who visited us since last year. And on the bottom, you can see this is the conceptual wireless solution for the so-called ultra-high-speed vacuum tube train, or Hyperloop in short. So we know when the train is traveling at a very high speed, like 500 kilometers per hour or even above in vacuum, it's not possible for us to power the train using pantograph anymore because of the large friction and the breakdown voltage inside the vacuum is very low. So instead, we have to go either for the battery option or to charge the train on the go. If we go for the battery, then the battery size would be huge because the power consumption is really high. It's in the level of a megawatt. So we propose this solution which can charge the train while the train is moving well in the region close to the stations. And there's a master student studying on this concept last year, and you can download its thesis by searching the name of the students and the title of the thesis here. So in the far future, we are looking forward to a world powered with green energy for transportation, and for the stationary charger, it enables us a scenario of park and charge without any hassles. You could just drive to the parking space and your car is get charged automatically. We are also looking forward to in-motion charging. For example, in this future green energy highway, if your car is running low in battery, you can just drive to the left lane to get charged. Well, in the far future, we are not only looking at the cars, but also at the buses, electric ships, and trains. Okay, that's the end of the presentation. And you are welcome to ask questions.
Well, thank you very much, Jianning, and also Pavol. If Pavol is still there, he can join us perhaps with his camera and mic on, if possible. So a very interesting subject and a very interesting presentation. Thank you for that. So with the questions, regard to the questions, from a consumer's perspective, you do not see much EV car makers already having offering wireless charging. So is the speed or lack of speed of this development a surprise to you? Does it surprise you?
Well, maybe I can start answering the question.
Yeah,
and if
please.
Pavol comes up with some new idea, he could compensate. So in my point of view, it's not surprising at all. You know, the companies are profit driven. So if there are no targets to buy, they wouldn't produce, right? No matter how advanced the technology is. And people do not want to buy the wireless charger. I think it's because they are not feeling the pain of charging yet. So if we check the cars available on the roads, not so many electric cars in portion, right? So maybe, well, 10% of these cars are electric cars or even less. And with the available chargers, they can get charged. But in the future, if all the cars are being replaced by the electric cars, we will run into the problem of available charging points. So you will see, well, charging poles along the streets and a lot of cables. And that would create a lot of problems. But with wireless charger, we don't see these poles, and you can just park your car there and you get charged automatically. So that will save a lot of effort. So yeah, to summarize, I think is it still too early for the well selling of wireless chargers because, well, people don't feel the pain yet. So people who are buying the electric cars, they don't mind plug in at the moment, but in the future it will change.
Okay, thank you. So if Pavol is still there, perhaps he can join us by putting on his camera and his mic. If he's not there, then we'll try to put as many questions to Jianning as he will try to answer. So another one which is also being put forward by Hugo de Almeida. I'm not pronouncing it right, probably. But is V2G, vehicle to grid, or bidirectional charging also possible with regard to wireless charging?
Okay, that is definitely possible. So I can show it by while going back to one of the slides I made. So the system here, actually you see here, this 20 kilowatt system is indeed bidirectional. So actually the bidirectional wireless charger works better than the unidirectional one because by adding the active controllers on both sides, you get higher efficiency. Okay. If you just use a unidirectional converter with diodes on the car side, the loss would be higher. So that's why to achieve this 97% efficiency, we use active controllers on both sides, and this improves the efficiency. And then the power flow direction would be just a matter of control. That's also why we are developing this grid interaction and the efficient power flow controller for wireless charger. So in the future, the car can also supply electricity to the grid back.
Okay, thank you. Another one is we all used to having inductive charging of our toothbrushes, for example, electrical toothbrushes, and some for our phones. So is this basically just the same, or is there a huge difference between charging a car or electric vehicle and your toothbrush? Well,
in principle, yes. So they rely on the same principle as we can see here. So actually the structure is exactly the same. We have an echo transformer in between, but there are some slight difference. Well, for the toothbrush, etc., you can imagine the distance is much smaller, right? it's easier to get the field shielded. But for the car, it's different. And for the toothbrush, we are not carrying them while charging, right? We just put it in our bathroom, that's it. But for cars, it's a battery on the wheels, it's moving, right? So when we are designing the charging system, we have to take that into consideration. And for the low power rating of the toothbrush, that although it creates some harmonics to the grid and to the neighboring electronics, the impact would be much less compared to the electric car charger you can imagine. So for the car, we need to deal with a lot of EMI related issues. So we need to make sure we are not injecting a lot of harmonics to the grid and also to the electronics in the car and outside the car. That's the main difference. Yeah.
And perhaps if we get to full autonomous driving, what will this mean for inductive charging? Will this be a huge impulse for inductive charging?
I think so. So in the future, if you have the robot, you can have the robot carrying plugs to charge these autonomous cars, right? Another solution is the wireless charging. But if you compare these two solutions, I think the wireless charging solution works better. On one hand, because there's no mechanical components involved. So no mechanical components means better reliability and lower maintenance cost, because you don't need to have the lubrication or anything like that to maintain a moving robot. On the other hand, it provides more flexibility. So you can do the charging on the go. So when the vehicles are driving automatically, we can charge it on the go. We can even monitor the state of charge in every vehicle, and we send this information to a centralized system so that we can control the power flow in a smart way, considering the routes of every vehicle. So that will enable a lot of possibilities by introducing wireless charging together with the autonomous driving.
Yeah, and so I remember we did, some parties did a test pilot in Rotterdam a few years ago, Rotterdam wireless charging. So one of the issues I remember is the space between the two parts is a huge thing. So if the car is driven a little bit off the charger, then you get more loss of energy efficiency. So we have some questions about that also, because Pavol told us the efficiency is there's no additional efficiency loss, but that's perhaps when there is not a lot of space between the two.
Yeah, so you mean if the car is not exactly on top of the charger, you may notice a big drop in the efficiency.
Yeah, that's my question.
Okay, well, so Pavol showed this slide a few minutes ago. So his point was the space in between the charger does not necessarily mean the additional loss. And what we see in the pilot in Rotterdam is that, if there is a lateral or longitudinal offset, there will be a drop in the efficiency. That is because of the drop in the field. So the power is transferred by the electromagnetic field, as we can see on the screen. So if the area drops, the overlapped area drops, the available area for the magnetic field to go through drops. Then we need to pump more current to get the same power. But you can solve this problem by doing some trade-off. Like I said, it's a conservative of misery. So if you want to get high efficiency for the misaligned case as well, there are few measures we can do. Like for this 20 kilowatt charger we have here, we took some measures. So the measures we took, including we have we have different sizes for the transmitter and the receiver. So
yes.
physically, it allows some alignment already. Then in the design process, we are not aiming at the optimization of the aligned efficiency. We are aiming at both the aligned and the misaligned. So you can see from the final, Pareto front of our optimization, although there are still some points showing both good efficiency and good power density for the aligned case, we still choose this point. That is because the efficiency drop because of the misalignment is not that much. It's only 2%. Although
okay.
we can choose some points on the left to achieve better power density, but you can see the points on the right. Sorry, the pattern on the right will cause a much bigger drop in the misaligned efficiency. So in the standard, it is required to have some allowance for misalignment. You can see it's in the x direction 7.5 centimeter, y direction 10 centimeter, and our optimization is actually larger. Our optimization considers a misalignment of 15 centimeter. So with this distance, it can still get efficiency above 94%, and that is comparable to the conductive charging. So the problem can be solved.
Okay, thank you. So Ben Whitfleet, he's asking a lot of questions, but let's select one. He works in radio communication engineering and research, and he has some concerns about the unwanted radiation. And can this cause serious interference with two radio systems, for example? Is there any data on that?
There's no simple answer to this. Let's again look at this electromagnetic spectrum. So the fundamental frequency and the main harmonics of the wireless charging system is far below the radio frequency. The radio frequency is from megahertz to gigahertz, but the frequency of the wireless charger is at 85 kilohertz, and the 10th harmonic is 850 kilohertz. If we consider even higher harmonic, it can reach the radio frequency region, but the amplitude will be much smaller. So with the proper shielding, it should not cause big problem to the electronics. But if you just put a coils there without a very sophisticated design of shielding, for sure it will affect the surrounding electronics because it can create the circulating current inside the electronics.
Okay, thank you. So let's go to some more questions coming in. Marcel Buters asks, to what extent does the shielding analysis differ for the unused standalone charging surface to the situation when a charging session is active?
Well, I don't fully get this question. Please allow me to rephrase the question. So my understanding is, your question is, what's the difference of the shielding effort for a standalone charging system compared to a system with several charging paths? Is that your question?
Well, perhaps Marcel can follow up to the question, and we'll get back to that later. Let's go to one other one, to Niels Vrijsen. What about other systems impacting efficiency besides in plain misalignment? For example, Z-range or of the underbody, vehicle integration and interoperability with the standardized coils?
Yeah, so there are many things can affect the efficiency. The misalignment and the z direction distance, for sure, they will affect the efficiency because they result in change directly in the magnetic field. Other issues could be like the power electronics converters we use. So to achieve the highest efficiency for now, we are not using silicon devices. We are using silicon carbide power semiconductors to construct the power electronics. The compensation will also have a big impact. We actually in the paper for the optimization of our 20 kilowatt system, we studied various types of compensation method. You could just use a capacitor bank to compensate it. You could also use a capacitor plus inductors. So these different types of compensations will result in different content of harmonics and also different level of efficiency. The ferrite, so how you arrange the ferrite for the shielding and the shielding material, whether you use copper or aluminum, they will all have some consequences on the efficiency. In the end, after the system is designed, how you mount it to the car will also affect the efficiency to certain extent. The chassis of the car itself works as a big shielding frame as well. So if you have shielding for the field, you will eat some energy from the field. So that will have some limited impact on the efficiency.
Okay, thank you. Another question by Tom Huisman, who thanks you for this nice presentation, by the way. The question he asked is, when looking at charging of large vehicles, buses, trucks, etc., how does the cost of wireless charger, including installation and ground, etc., compare to a regular charger in the near future? For most operations, it will be mainly a matter of costs to move forwards in this technology. And let's add the question of Danny Post also. Do you think this is a chicken and egg problem? Car producers waiting for the charge points and the other way around?
Well, let's answer these questions in two steps. First, how the cost increases for the heavy-duty vehicles for larger charging pads. Well, unfortunately, I'm not a commercial guy. I don't study the cost because the cost itself involves so many parties. What we can do is just we get the BOM list and calculate the material cost. But you know the material cost differs a lot. If you order them in bunch, it drops a lot. So we are not able to give well the full spectrum cost from the material to the manufacturing to the selling. So that's not our task. But what I can tell you is with this multi-objective optimization, we can reduce the cost a lot. If you just take the standard designs, it meets the requirements, but probably it does not give you the best power density. By power density, I mean the power over the area, which is well important for cost reduction, because the larger the pads, the more ferrites and the copper you have to use, and the more least wire and the ferrites you put there, the more man labor you have to spend on it. So so that's why it's important to have the well the best solution with a compromise between the power density and the efficiency and etc. So I think there is a potential to reduce the cost in the future for sure, if we design carefully. And the second part of the question is the chicken and egg problem for the charger and the marketing, right? So I don't think it's a chicken and egg problem. It's more like, well, we are still at the baby age of transportation electrification. It's so we just came out of the egg. we are not yet a full-size chicken yet, so it takes time to reach that stage. Maybe in 5 years or 10 years, when 30% of the cars on the road are already electrified, we start feeling the pain of plug-in charging. And afterwards, there will be more and more wireless chargers deployed on the market.
Okay, thank you. So Bagas Ishan Primambo, sorry for the pronunciation, Bagas, is asking us, how does on-road wireless charging affect battery life? I assume there is more charge and discharge cycle.
I have limited knowledge on the battery lifetime, I have to admit, but from the limited experience I have, to extend the lifetime of the battery, we have to avoid deep discharging. So we have to make sure the DOD is not that deep, or the SOC is always within certain range. And that's what the dynamic charging can help. So if you make sure that the battery is not always discharged well to its maximum capability, we can actually extend the lifetime. In the meantime, if we have the dynamic charging, we can also reduce the size of the battery inside the electric car. And well, in this way, it helps the circularity of batteries. And well, in a large range, it can reduce the overall cost of an overall material consumption on the battery.
Okay, thank you. Due to the time, we have just a few more questions, and then we'll have to end this webinar. But there are more questions than we can answer right now, so we will send them to you, Jianning, so you can perhaps answer them via email. So one thing from Elaad also, we're doing a lot of research in smart charging, because we want to make sure we use the optimize the use of the charging time. So is there any research done already on inductive charging with the combination of smart charging? You already told something about vehicle to grid, which is a great combination, you say, but also charging at a later moment, charging at a different speed. Is that possible?
Yeah, of course. Whatever you do with wireless charging can be implemented in wireless charging. We got some projects on the smart charging for conductive ones, but the same thing, the same algorithm can be applied there. And in the project progresses in collaboration with the ElaadNL, in that project, we are also required to do some demonstration of this wireless charger in a big system like a DC community or something, as one of the work packages. And there we will demonstrate wire simulation to show that this is feasible.
Okay, thank you. So let's do this one as the last one. This is from Jaap Verhaag. What do you think are the biggest hurdles for wireless charging before OEMs, electric car manufacturers, will move to new electric cars having this feature, wireless charging?
Okay.
So any last thoughts on this one?
Well, it's yeah. Again, I'm not a commercial guy, so that's this question is not in my comfortable zone, unfortunately. But I'm happy to answer. So my opinion for now is the reliability of the system. Because if I run a company and I'm selling this product to the public, I bear the liability. And for the conductive charging, well, all the technologies they are available, and I'm confident that this would work. And the cost is also lower. And I don't face the public concerns about electromagnetic field, etc. So I can just sell them. But for the wireless ones, there are some hurdles like this. I have to convince the public the electromagnetic field is not doing anything harmful to you and to your car. And I have to bear the cancer. It does not cause cancer.
Yeah, in Rotterdam we talked about cats.
Yeah.
Pets.
Yeah. I also need to show them, well, even with the addition component, the reliability does not drop. So if I can do this, probably it can help.
Okay. Yeah. Well, thank you very much for your presentation, and also Pavol. He was not able to answer the question, but Jianning did a great job, I guess. And very good luck to all your research in the near future. Thanks also for all the attendees and for all your questions. The next web talk we do is in 2 weeks' time. It's the 24th of March, and it's about interoperability and the charging of electric planes. So a lot of different angle. This web talk will soon be available on YouTube. And thanks again, everyone. And we hope to see you again in 2 weeks' time, same place, same time.
Thank you. Bye-bye.